Okay, I'm going to again try to amaze you. I may not succeed, but when I'm amazed, and I'm still amazed, then I figure one or two people out there could be amazed by what I have found. First of all, I just want to point your attention to this active region turning in. If there was a stream of particles coming by the sun and right at the camera, then as this active region turned in, you would have more particles to shine the light through. You would have a better viewing angle because you put a light source that's directly 90 degrees to the density. So then all of a sudden the density starts to glow better. You see more reflections off the particles. But also the concentration of particles themselves increase. And notice as this active region turns into that high density, notice how the light gains out into the corona, how the loops project and start to glow and become more obvious the further out in the corona as this thing turns into that high density region. This should be happening on both sides of the sun. If we're downstream and like in this little pocket hiding behind a rock in the current, and you could look out and see the current, then this is what would happen. And the active region itself, as you notice, looks like a giant whirlpool. You're actually looking at a funnel, and you're looking up underneath at the underneath part of the funnel, and that funnel is slowly turning towards you, and it kind of makes like a little ceiling or a little ramada or roof that you're actually looking underneath this loop that's spread out. But this should happen on both sides of the sun, where as the active light source turns into the high density particles, then all of a sudden the corona should start lighting up more. And then I noticed the 1600 angstroms, which is 160 nanometer. It's a high energy ultraviolet. Ultraviolet C starts about, they call 250 nanometers. They call that ultraviolet C, but extreme ultraviolet goes all the way down to much lower nanometers. But this is 160 nanometers, and 160 nanometer radiation, those wavelengths in that region have been climbing for decades now. So when you start seeing flashing in the corona at 160 nanometers, you're like, hey, I think we found the source of our 160 nanometer increase. It's the corona of the sun. So what do? They dim the aperture on the 1600 angstroms on SDO satellite, and now you can't see the flashes, and then we have to use special techniques to bring out that data, and we still show the presence of those particles flashing in the corona called pinpoint emissions. Look it up. That's gamma radiation, visible light, extreme ultraviolet, heat, infrared, all being produced in a single flash from particle collision. There are X-rays also. From when electrons do funny things, they release electrons. The electrons themselves release X-rays. But they're capable of any wavelength. Electrons, no matter, depending on what you do with it, emits all kinds of different wavelengths, from low energy electromagnetic energy to high energy gamma, all produced by our little electrons. But these are pinpoint emissions. And the 1600 angstroms, they upped the aperture setting. Actually, the SDO thumbnail was glowing brighter than I'd seen it in 3-4 years. And I'm thinking, oh, well, I guess they're not going to hide the particles. But they overcompensated. They extra brightened and the time lapses are longer. So what you need is a high-speed camera, lots of frames per second to pick up these flashes. So now you don't see as many flashes because the time frames are elongated, and now they're over apertured. But that kind of washed everything out. So now we've got to do another technique to try to find these particles. And we do find them again. There they are, flashing in the sun. It's not rendering as effectively as we could with the under aperture setting, but yet the particles are still there, but it doesn't look like there's more of them. And this is actually the actual hard footage. Notice how the background's glowing green. That's an overcompensation on the aperture, washes out the background stars, which are really pinpoint emissions, particle collision. A filament building on the sun. We're going to do a whole video on this thing as it turns in. Helium viewer, of course, running behind, so wait for that. And we're going to actually show you the corona under special rendering. Well, here we have another active region turning into high density crest, and look what happens. The filaments, especially the ones further out, twist, figure 8, and you see many different orientations to your magnetic field line. And as it turns in to the high density particles, all of a sudden the loops start to illuminate further and further out into the corona, which is what you would expect when your light source turns into its highest density of reflectivity. So and all of these high energy, extremely high energy. This is very high energy, ultraviolet. These are particles that are making this glow that comes off the sun. The light that you see is in 17 nanometer. You're actually seeing an intense radiation. So if you have a computer screen, tilt it back now, as far back as you can, and you can see the layers of particles now. We had to do special rendering to try to bring out more definition to the particles, and now you can see the layers. So whenever we do that special highlight, reverse light, you have to tilt the screen back, but this is a close-up of that filament, and look how beautiful and strange it is. But notice the glowing in the background. So again, we do the particle highlights, the inverse of the color, and tilt it backwards, and you can see underneath a layer of particles that is hovering in the solar corona. When you take it off the rendering, those particles, you can't even see them. They're basically invisible. And we just showed you the atmosphere of the sun as you could see it if you were standing on the sun, and you see the particles, and you can see the undulations and the rippling in the actual medium. And we're going to kind of keep trying to work with this program to show you these particles. Remember, you've got to be measuring more than 30 billion particles per cubic meter, because the sun's strong gravitational field has to focus these particles into such high densities. So 30 billion is really conservative. So let's go to this side of the sun. Again, you see some of the glow coming off the sun. And notice it's not coming out straight out from the sun. Notice it's being bent and warped and wrapped. These particles are actually being drawn in from the corona. And if you tilt your screen back again, this is just a tremendous image I hope you have a large screen computer. You can tilt the screen back. I don't know if you can do it on the phones, but you can see with intense detail what the energy is doing. These are particles under 17 nanometer radiation. So this is 17 nanometer radiation. This is high, extreme energy. Now here's 193 angstrom. This is 19 nanometer. I mean, this is approaching X-rays. And we know particles are creating this glow. And we were able, when we pulled away from the horizon, we actually got better detail on the layering and the motion of those particles. But notice all the flashing, notice the undulations. That's just a remarkable, that's just incredible rendering of the solar atmosphere just above the horizon. This is amazing. You're looking at particles that are invisible to most human beings because of the way we rendered. We just got high definition contrast, and look at that. That's just amazing. Amazing. Just, I'm flabbergasted just watching this over and over again, that we can actually visualize what's causing all the problems. You're looking at it. It's like staring at a guy with a gun as he's pulling the trigger. You're seeing, you don't need the smoking gun anymore. You've got to picture the guy pulling the trigger on video. I mean, it's right there for you. I can't put anything more obvious in your face. So we had the same anomaly showing up on both sides of the sun as these active regions turned into the highest concentration of downstream particles, where ionization occurs. Well, now you got to tilt your screen forward and look at the corona of the sun. Look at that checkerboard appearance. Oh, my. Well, this is 33 nanometer. This is the ionization of helium. Helium loses its first electrons. It releases that radiation, the 30 nanometer radiation. And if you have two sources of helium now, traveling in completely opposite directions, you have completely opposite spin and wavelength orientation on your photon emissions. Visible light has wavelengths. You can see the gaps in those wavelengths. You can hold your fingers up close to your eye, your fingers together, so you can just barely see through the cracks. And you'll see 9 or 12 shadowy vertical lines running in between your fingers. That's the wavelength of visible light. The actual wavelength. But this is the wavelength of 30 nanometer light, which is invisible to you but harmful. Extreme ultraviolet. 30 nanometer ultraviolet can hurt you. So we have two sources of ionization, and we know where it's coming from. So now we're going to subject the incoming limb to some rendering. Tilt your screen back, and oh my, if you don't watch this in full screen and tilt the screen, you are missing out on an incredible image. We speeded it up to show you a time lapse of what these particles are doing. They're behaving just like you would predict high concentrations of particles to behave, just like fluid dynamics. And you can see where the vortices are concentrating even higher concentrations of these particles. Amazing. Just amazing. So So you wonder why the sun is so bright and hot. Well, 30 billion particles per cubic meter is just very, very conservative. Here we go. Tilt your screen back. Check this out. Look, it looks like just sheets, and this is what I've described the interstellar medium as: sheets rolling upon one another, obeying fluid dynamics, hydrodynamics, gas dynamics. Very basic laws of physics. But again, as we turn into the high densities, just the corona, the outer part of the frames, just light up. Where it's used to be dark is now glowing at the edge of your frame, proving where the highest densities are of these particles. And you look at the twisting, you look at the undulations. There's nothing here that would debunk the notion that we're downstream from a second source of solar wind, a second sun's wind. They call it the interstellar medium. Thousands, if not millions, of pages of research on the interstellar medium, called the hot bubble, the hot gas bubble, the gas bubble, the helium bubble, the hot helium bubble, the helium cloud, the hot gas cloud. All of those you can look up to describe the same thing. So then on 625, if you were watching real time of this chronograph and they would just put it up on time, you could have ran online and said, the sun's going to chain react. The sun, watch out now. Just keep an eye out. The sun's going to chain react. And you can see all the collapsing cavities coming in from almost all directions. And then what happens the next day on 626? Let's all say it together. Kaboom! You would have made yourself look like a genius. And you really wouldn't be a genius. You would just be a subscriber to the higher truth. So we're looking at the same exact flare. I think it's an M flare on stereo A. Very high speed ejection. Remember, I said these collapsing cavities cause high speed, highly reactive, instantaneous eruptions. You would have looked like a genius. Anyways, then on stereo A, we notice this flashing. We're just running it back and forth, trying to decipher why this would even exist, unless they're slapping on additional filters. I don't know what would cause that flashing, unless you're talking about electron discharge through plasma. Now, we showed you these earlier. These are when you search what the density of particles are in space. We don't see high densities. We see particle densities of 5 particles per cubic centimeter. But when you convert cubic centimeter to cubic meters is one thing, but when you convert 1/1000th of a cubic centimeter to a cubic meter, that's 10 to the 9. That's a billion particles. Speaking of a billion, that's $1 billion question. If I just showed you 10 different accounts of what particle concentrations are supposed to be throughout the solar system, and then I showed you the concentration of the second sun, and its particle concentration may be different in composition, but density is very impressive. 10 to the 6 average density of the cloud, so it has higher densities and lower densities. 10 to the 6 particles. Use the word particle and proton interchangeably, which is incorrect, because there's so many other particles in the solar system right now, including iron, dust, lithium, all these particles atoms running around. It's a soup. But the soup is flowing mostly in one direction. Now, all of a sudden now, a bunch of phenomenon starts to make a little more sense. The green flash that, like, the entire solar system, it seemed like, flashed green like a giant flashbulb back in the transition from solar max to solar minimum. And the flash was caught on various cams around the world, including the ISS. So you can't say it was a refraction thing of the sunset. But when I'm seeing, up to 30 billion particles per cubic meter, it explains a lot. Now, and the way the layering of the atmosphere of the sun can all be explained now. I mean, look at Jupiter's atmosphere, the striations, the banding, the separations. Well, the sun's atmosphere has to behave the same way. There's outgoing energy. There's outgoing waves. There's all kinds of outgoing force to try to push particles away from the solar surface, creating a cloud layer of particles. And this explains so much, proves so much. A lot of the explanations have already been put forth, but the ringing in the ears, the extreme heating of land, but not air, caused by basically photon radiation. A layer of particles over the sun like a cloud cover. Now, that would then create more energy in the sun, more particle collisions, a lot of flashing in the corona.